Okay, so we take the derivative of a distance time formula or graph, you get instant velocity. Okay, now we're going to move this up one more notch and we're going to talk about acceleration. Okay, now average acceleration, which is something that you find in physics, is the rate of change of an object object's velocity with respect to time. So the rate of an object's velocity, rate of change, of the object's velocity with respect to time. Okay, so acceleration average would be delta V over delta T. Change in velocity over the change in time. So that's VF minus VI over TF minus TI. Okay, the units are meters per second or meters per second squared. Okay, now the beauty of knowing how to find a derivative is you can find the instantaneous acceleration. Now, when acceleration is constant, average will work for you all the time. Okay, it's when you're in a real life situation, and if you've ever driven anywhere, I guarantee your acceleration is not constant. Okay, there's passing, there's stopping, right? There's slowing down. There's tons of stuff going on. Now, if you just took your time and the distance after the entire trip, you could find your average. But what if you wanted to find it at any specific time? Then you would use your derivative for instantaneous acceleration. Okay? Now, instantaneous acceleration is the derivative of the velocity function with respect to time. So if you were ever given a velocity time graph, right, you would be finding acceleration, you'd be finding the slopes, right? If you were doing a distance time graph, that's going to be a whole other set of rules. So we're going to learn both of those today, and it's going to be your job to figure out how am I going to make sure I don't get a distance time graph mixed up with a velocity time graph. Okay? I think if you're given a velocity equation, you're just going to take the derivative of that. If you were given a distance equation, you would take the derivative and then the derivative again. So most times with the equation, you're probably not going to mix it up, but will you know your rules for your graphs? Now, when it comes to instantaneous acceleration, we want to do the limit. So the limit as delta V over delta T. Now that looks like a average acceleration. But if we take our delta T and we get it closer and closer to 0, we will be getting dV over dt, which is V prime t, okay, the velocity. So remember, as we get that change in time smaller and smaller and smaller, we get closer and closer to getting an instantaneous acceleration. Now, if it's a position function graph or a distance time graph, acceleration is d d2 over dt2, which is s double prime t. Okay, so make sure you're doing the second because that's supposed to be like displacement, right? S, not speed. Velocity. Okay, we're not going to be talking speed. Okay, now this is where things are going to get where you got to keep things really straight. Acceleration describes the rate of change of velocity with respect to time. If acceleration is greater than 0, then the velocity is increasing, but not necessarily speeding up. And if acceleration is less than 0, then the velocity is decreasing, but not necessarily speeding down, or sorry, slowing down. Now, it could be by increasing, let's say that it's going north or east. And if it's decreasing, you could say that it's like going south or west. So the best way I can explain it, if the acceleration is going in the same direction as the velocity already is, okay? Like when you have two boys that are running around the house, as in my life, when one's running and the other one's chasing them, and they push them from behind, okay? They're pushing them in the exact direction. They're accelerating them in the exact direction that they are running. Therefore, they're not ready for the wall at that point, okay? They were ready before the push, okay, or the cabinet that was there, or the doorknob, or whatever, right? Now, and then the wall is providing the negative acceleration for them, okay? And you can see that's in the opposite direction, okay? So the important thing is to always see, okay, if it's going down and gravity pulls down, oh, it will speed up. If you shot a rocket up with gravity pulling down, that should start slowing down. Okay? So, just to kind of just do an example, you guys should know that gravity is negative 9.81 meters per second squared. So, when an object is going up, it will slow down. Why? Because the velocity is opposite to the acceleration. Therefore, that is something that has a positive velocity but a negative acceleration. Therefore, it will be slowing down. Okay? When object is dropped, it will speed up. Okay? And in fact, if it was dropped in a vacuum, it would never stop speeding up. Okay? Every second, it would get 9.81 meters per second faster. Because they're both going in the same direction, we've got a negative velocity. We would have a negative. Now, we really got to, is negative velocity mean slowing down? No, the negative is the direction. Okay? So, negative direction, or negative velocity, negative acceleration, that thing will be speeding up. So the way that you'll be able to remember it, if V and A both have the same sign, it is speeding up. If V and A have an opposite sign, it will be slowing down. Okay, so say we have something that acceleration is positive 4 meters per second squared. Okay, so let's just do a velocity greater than 0, and of course, let's do velocity less than 0. Okay, so let's say the velocity right now at 0 seconds, let's just put it's 10, positive 10 meters per second. After 1 second, what should be my velocity? 14. Because every second it is getting better by 4 meters per second. And after 2 seconds would be 18. See, A is greater than 0 and V is greater than 0. So object is speeding up. Okay, now what if we had a velocity of negative 10 meters per second? Okay, so say you were traveling west, negative 10. If you had a acceleration of 4 meters per second, what would negative 6? So what would be an example of a force that would, what could you do to a vehicle to give a negative acceleration on it? Or, sorry, in this case, a positive acceleration if you're going west. Yeah, put your foot in the brake. Okay, we'll hit a pole. I think you're, yeah. Okay, and then the next one would be negative 2. So in this case, A was greater than 0, but V was less than 0, so this would be slowing down. Okay, so now if you have something acceleration negative 3 meters per second, now again, some people go, oh, there you go, you got something that's braking. That's just slowing something down. Okay, but the direction the velocity is moving is important. So if velocity is greater than 0, let's say it's 10. Okay, if I was doing negative acceleration on that, the next speed would be plus 7 and then plus 4. So in this case, A is less than 0, velocity is greater than 0. This would be slowing down. Okay, velocity is less than 0. So if we were at, say, negative 10 with a negative 3 meters per second in the negative direction would be negative 13. And then again would be negative 16. So this would be acceleration was less than 0, velocity is less than 0, this would be speeding up. Okay, so the position of a particle is given by, so now this is always crucial when you see this, the position. So this is a position or an S equation. So S equals t cubed minus 12t with S meters and t seconds. Find the acceleration, okay? find the velocity, I would do one derivative. To find the acceleration, I will do the second derivative. So let's do velocity. Velocity equals s prime, which would give you, should be able to do these quick now. What would it be? 3t squared minus 12. Acceleration is s double prime would be 6t. Okay, so now acceleration at 3 seconds would be 6 times 3, which is 18 meters per second squared. Acceleration at 5 seconds would be 6 times 5, would be 30 meters per second squared. So find the acceleration when velocity is 0. No, because if I went back to here, look at this one, I would get to 0, right, if I kept going with this chart, but my acceleration would still be negative 3 meters per second. Okay, so it's the point where you got to that, but you were applying the brake the whole time, right? What acceleration were you going to get to 0? So when velocity is 0, well, when is velocity 0? So the when you're looking for the t when velocity is 0. So if we use this, which we already found, well, let's go 0 velocity equals 3t squared minus 12. Okay, 12 equals 3t squared divided by 3. 4 equals t squared. Take the square root of both sides. You'll get plus or minus 2 equals t. Now, because we're never going to be dealing with negative time, we will say we will reject negative 2. And t equals 2. Okay, and for this time, we'll just say can't be negative time. Can't really have south time. Okay, so at 2 seconds, we just have to find out what the acceleration is. Well, we know that a equals 6t. A equals 6 times 2, which is 12 meters per second squared. So I was accelerating at 12 meters per second squared when I hit the velocity of 0. Okay, so the position, still at that, of a particle is t to the 4 minus 12t cubed plus 30t squared plus 5t. When is acceleration positive? When is it negative? Okay, well, let's get the velocity equals s prime, which would be 4t cubed minus 36t squared plus 60t plus 5. Acceleration is s double prime, which would be 12t squared minus 72t plus 60. Now, to get some bearings, we want to find out critical values. Now, if things are going from positive to negative, I guarantee they had to go across 0. Okay? So, we want to find the zeros, aka critical values. So 0 equals 12t squared minus 72t plus 60. First thing you should always do, take out something. We can take out a 12. Leave me with t squared minus 6t plus 5. Zero equals 12 times, two things that add, t minus 5, t minus 1. So my CVs are 5 and 1. So that's when acceleration is 0. So when is it positive and negative? Well, it's not at those points, but it's all the time intervals in between that we have to test, okay? So we want to get our number line here. We want to put 1 here and 5 here. Now there's something very different about these graphs that we've never done before, is there actually is another critical value on here that is implied. Yes, 0. Because we're never going to be doing negative infinity to this and whatever, because there's not a negative infinite time. Time is going to start at 0. Okay, so something to keep in mind when you're doing these. So we want to do test values. I always write my test values down on my page. That way, when I want to come back later, I can check them. So 0.5. Now all you have to do is put, now when it's a positive up front, I kind of ignore it, but maybe to get in the habit, because if there was a negative out front, you don't want to ignore it. Okay, so let's just to get you in the habit, okay, there will be a positive there. Now if you put in negative 0.5, or sorry, if you put in 0.5 in here, do you see you will get a negative, right? So you put your negative there, and then if you put 0.5 in here, you'll get a negative again. And all you do is multiply them together, a positive times a negative, and you will get a positive right there. So you're plugging it in to this equation, and you're picking a test value. Okay, a nice one between 1 and, let's do 2. So you got a positive there from our positive 12, and then 2 minus 5, that's a negative, and 2 minus 1, that's a positive. So positive times a negative times a positive is a negative. Okay, let's pick 6 for our test here. We've got a positive, positive, and a positive. Give me a positive. Okay, so how would we write this? We would say, therefore, acceleration is positive square bracket 0, comma 1, and we'll put a round bracket there, union 5, comma infinity. Okay, so we can put a square bracket around 0 because it could be greater or equal to 0. Round bracket around infinity, of course, because we never reach it. And then acceleration is negative at 1 to 5. Okay. Now let's talk about the acceleration on a velocity time graph, okay? So if anything that is going to mess you up is if you don't read what it is. Because if this was a distance time graph, obviously we would read it very much differently, and they're the harder ones to read when it comes to acceleration. I would say harder. You've got to know more information, and we'll talk about that next. The velocity time graph is the easiest because it is the derivative of velocity. Okay, when we're finding the first derivative of any graph, what are we always finding? Slope. Okay? When we're finding the second derivative of any graph, we're always finding we're actually finding sort of the slope of the slope, or when slopes are increasing and when slopes are decreasing. Okay? So if this is a velocity time graph, so describe the motion. Okay? So we're just going to describe when acceleration is positive and negative. So from A to B, what would you say about acceleration? It's positive, right? And you could just draw a slope in there, right? So A to B, I would say A is greater than 0. Okay? What's happening at point B? So B, you would say acceleration equals 0. B to C, you have negative acceleration. Acceleration is less than 0. C, we would have acceleration equals 0 again. D, acceleration is greater than 0. Oh, sorry. C to D. Okay, that should make sense, right? That's not a huge leap. So the more difficult are the position, acceleration on a position time graph. So don't get these mixed up with a velocity time graph. So on a position time graph, how do you know if there's positive acceleration? Now, by looking at a graph, not by doing a second derivative, but by looking at a graph, the slopes, aka velocities, are increasing. Now, how does that look? Like, how does it look when slopes are increasing? Like, relative to what, right? So, say you had a graph that was like this. You see the slope here? You see how those slopes are increasing? Those are increasing slopes. They went negative to 0 to positive. Those are increasing slopes. Okay? So, this happens when a graph is concave up. Okay? And it's like a smile. So I'm going to put little positive eyes there for you. See? Positive. Positive eyes. Now when you have negative acceleration, your slopes, velocities are decreasing. So if you had something that looked like this, do you see how we've got a pretty positive slope? Getting a little less positive, a little less positive, 0, negative, more negative, okay? Do you see how this guy's very sad? That is concave down. It's like your umbrella. It's sad when it's raining. Now when you have zero acceleration, what would you expect zero acceleration? Constant slope. Very good. Okay, so that's when the slopes are constant. What does a constant slope look like on a graph? Straight line. Okay, so if you drove to Calgary at exactly 100 kilometers an hour, that is zero acceleration, right? So the hard part will be maybe just looking at a distance time graph and saying, hey, when is it speeding up? And that's not just done by looking at the graph. You're going to have to, okay, so we want to look at this graph. I want to know when it's speeding up. I want to know when it's slowing down. So let's do like a chart here. Okay, so let's do velocity here and acceleration there. And let's do, okay, we got A to B, we got B to C, C to D, D to E, E to F, and F to G. Okay, so from A to B, now remember this is a distance time graph. So what are my velocities, positive or negative? Positive. Now the acceleration, are the slopes increasing? Yes. Okay, so it is concave up, right? Do you see how you don't see this part of it, but do you see this is a concave up? And only in concave up would slopes be increasing. So we could say it's concave up. So yeah. And I'm even going to put this here. Like my slope is, they are increased, like it's positive, right? It's going uphill. So when you have your positive velocity and positive acceleration, this would be speeding up. Okay, let's go from B to C. My velocity, positive or negative? Positive velocity there, right? What about my acceleration? Okay, because we're concave down. Or actually, we can just start doing this, right? Concave down, that's concave up. So that's negative. So that would be slowing down. Okay, let's go from C to D. C to D would be negative velocity, right? And negative acceleration, because it's concave down. That would be speeding up. Okay, D to E, negative velocity. Yep, positive acceleration because it's concave up. So this would be slowing. E to F would be positive velocity and positive acceleration. It's concave up. So that would be speeding up. Now F to G would be what kind of velocity? Positive velocity and 0 acceleration. 0 acceleration will be a constant speed. So we should just make sure you make a note of this, right? So this would be a constant v then. If you're not changing the acceleration on something, it will stay the same velocity. Now where does velocity equal 0? Yeah, C and E. So just a few things to keep straight. But you can't really right away say if something's speeding up or slowing down till you do the positive or negative velocity and then concave up. No. See, my acceleration is putting me past a 0, right? So like we did that one example. So it's, at something, if it is still, right, I would say, yeah, acceleration is nothing too, right? But if it's moving past 0, then, okay, so that's it, right? All good? Okay.